right, 27. Oh, I did want to say that the reason that these are numbered this way and these are numbered this way, this 1.4 and the 1 points whatevers, those go along with AP Classroom. So if you were to go into AP Classroom and you look at the 1.4 stuff, that goes along with this lesson that we did on 1.4. So I have numbered these with zeros because these are kind of going back and filling in some stuff before we talk about whatever it is that's going on in that lesson. And with the stuff that goes on in 1.5, I feel like there was a whole lot of, you should be super experts at this stuff and here's what we're doing with it. And although it shouldn't be new to you, I think that we needed to kind of go over it some before we just jumped into it. And so that's what sometimes these will look like. And, or it may not even be necessarily review things, it just may be things that I feel like need to be filled in that don't necessarily go exactly along with what they're doing. Because as far as content's concerned, we're teaching the same thing I've taught before. It's just kind of in a different order, and sometimes the questions are asked differently, so I'm still trying to get a feel for what their thought process is in all of this, and I feel like there's some things kind of missing before we jump into things. But so not saying this stuff wouldn't be on the AP exam, it's just not on there like purely like this. It's going to be within something else. So that's why this is 0.2. All right, so you won't find a 0.2 in the AP Classroom. So let's talk about zeros. Okay, so our different words for zeros, we could say we have zeros, that's one of them. What's another word for zeros? Roots. Okay, I heard roots. I heard x-intercepts. Anything else? Solutions. Anything else that you can think of? Those are the four that come to my mind. But zeros, roots, solutions, x-intercepts, those are all the same thing, right? Sometimes they're written a little bit differently depending on what you're asked for, but it's still just talking about where are we crossing the x-axis, right? Okay, or where are we intersecting the x-axis? So this kind of use all the little terms here. The x-intercepts of a function are also called zeros. So stuff we kind of already know, right? So a polynomial function of degree n can have at most n real zeros. So a polynomial has n zeros, period. But it doesn't necessarily have n real zeros. But the most it could have would be n. So yesterday when we did some of those factorings, we had a 5th degree polynomial. We ended up with 2 imaginary roots and 3 real roots, okay? So it was a 5th degree polynomial, but we only had 3 real roots, but a total of 5. Okay, so that's why it says at most, because if we're just talking real ones right there, but we're going to be looking at both. So if I have an even degreed polynomial, it has an even number of real zeros. So if I have a 4th degree polynomial, I'm not going to have 3 real zeros and 1 imaginary zero. It doesn't work that way. We'll talk about why more towards the end of this lesson. And then if I have an odd degree polynomial, it has an odd number of real zeros. And again, we'll talk about why once we actually talk about the imaginary parts. Okay, so another part of this whole factoring, zeros, whatnot, is the multiplicity that we have to look at. So the multiplicity of a zero is the degree of its corresponding linear factor. So when you factor something into like x plus 2 times x minus 3, those two things, those are linear factors because individually they are linear, right? That's why they're called that. So we are going to, just like we did yesterday, find the zeros, but then we're also going to talk about the multiplicities. So I have f of x equals this trinomial function, so I'm going to set it equal to 0. Do I have a GCF? Yes, x. So I get x, and then that gives me x squared plus 10x plus 25. So then I need to factor that leftover trinomial there. A is 1, that's phenomenal, so this will give me, I can jump to my 2 parentheses, x and x. 25 is positive, so the signs are the same. The 10 is positive, so they're both positive. What are my 2 numbers? 5 and 5. which means a more efficient way to write my answer would be x times x plus 5 squared. Okay. So when I look at this, I have, and if I looked at it from here and I solved them, I would get 0, -5, and -5, right? And so I know you know that when you list them out, you don't put -5 twice, right? But that's because the -5 has a multiplicity of 2. So the multiplicity part of that might be kind of new for you, but I think you already understand the fact that it could show up more than once, right? So when I give my zeros here, let's say x equals, well, I have this first one gives me 0, right? How many of those do I have? 1. So in parentheses, I'm going to put the multiplicity, but I'm going to abbreviate it as MULT period because it's a long word. Multiplicity 1. And then the -5 has a multiplicity of what? 2. And it says it's the degree of its corresponding linear factor. And it shows up twice. That's all that means. So even though I'm listing 2 numbers, this is a polynomial of degree 3. I have 3 real zeros. This one is just a double root. That's all it is. Okay? We're good on that? So even though there's 2 numbers, there's still 3 zeros. That makes sense to you? Are we awake? Yes? Okay. I'll take that as yes. All right, so then let's factor this one. What's my GCF? -x squared, good. So that leaves me with x squared plus 6x minus 9. So 0 equals -x squared time, then I can do my little parentheses. I got x and x. Oh, wait. I messed up all my signs, didn't I? Dang it. And that was even going to be something else. See, I was doing this on purpose. Make sure when you're factoring out the negative that you pay attention to your signs, unlike what I just did. So when I factor out the negative, and none of y'all stop me, I don't think you are awake. Those should be opposite. We good? So now, since 9 is positive, my signs are the same. Since 6 is negative, they're both minus. And what's my number? 3 and 3. And by the way, both of these trinomials that we're factoring are a special case. That's why we're ending up with the same numbers. They are perfect square trinomials. So if you know your patterns and you see this, and you can see that you take half of b and square it and get c, then you can jump right to 0 equals -x squared times x minus 3 squared, and you don't have to do this part here. But if you're not a person, but tricks and shortcuts and whatnot, those are all great if you remember them and you can use them right. If you don't, it's not the end of the world because it's not difficult to factor. So as long as you know after this, you write it like that, you're fine. So then my zeros, so x equals, this first one gives me 0. What's the multiplicity? What's the multiplicity in this one? 2. Do you have a question? Ask me if you have something. Do you have something? No? Okay. And then 3 with a multiplicity of 2. We good? Questions? Nothing? Okay. So let's see what this multiplicity does to our graphs. All right, so it says to, we're going to write this in factored form. So write this in factored form. So I'm going to factor it over here. It's not asking me to find the zeros. It says just write it in factored form. So over here, f of x, my GCF is x. So that leaves me with x squared plus 4x plus 4. I'm going to use my perfect square trinomial knowledge and get x, and I can take half of this and square it and get that, so that makes this x plus 2 squared. So my factored form, f of x is equal to x times x plus 2 squared. So it tells me to graph the function and look at the multiplicities, how they affect the graph. All right. So let's talk about some things that we should know about this graph already. We know that it is a third degree polynomial, so we should know something about the end behavior, right? The end behavior model is the end behavior of what? Is it a parabola? Or is it what? The even numbers model the parabola, the odd numbers model your cubic parent function, right? So your cubic parent function, the end behavior looks like this, right? This is what a cubic looks like. So this is a cubic, but that doesn't mean that it looks exactly like this thing, okay? But the end behavior does. And the only thing that would change it from this to this when it's an odd degree is if this leading coefficient was negative, and it's not. So I know that my end behavior looks like this. We don't know what's going on in the middle yet, but that's what the end behavior looks like. That's something we have to know by looking at that, okay? So then I also know what my zeros are. My zeros are, this would give me 0 and -2. You agree with that? So now we're going to graph it. We're really going to sketch it. Sketch is a little bit more sketchy, I guess. I don't know what to say. So I'm just going to do like 2 hash marks here, 2 hash marks here. So I have a couple of x-intercepts. Tell me, what is my y-intercept? Your y-intercept is when x is 0. So when x is 0, what is y? 0. If I substitute in 0 right here, I'm definitely going to get 0. Plus, if you ever have 0 as an x-intercept, that's also your y-intercept. It can't be anything else. So I know that I have an 0 and -2. Those are really the only intercepts that I have on my graph. Okay? Now, this next thing that I'm going to draw, I don't want you to draw. I just want you to think about this, and then we'll do it. So I know that my end behavior should look like this, right? Down, up, because this is an odd degree. If it's an even, it's up, up, or down, down. If it's odd, they're opposite. And so if I know that I start down here, and these are my 2 x-intercepts, if I come up and then I go back down, I don't have another one to come back up, and now this looks more like it should be an even degree, right? So something's not right here, or maybe it's right, but the fact that I have a multiplicity of 2, oh my gosh, the fact that I have a multiplicity of 2 right here means something. So at this -2 right here, something's going on. These are still x-intercepts. I'm still intersecting, I still have an intercept, and I am intersecting the axis. But if I start down here, at the -2, I'm going to bounce off and then come back up, and it actually looks like that, but pretend like I hit that point better. Okay? And you can sketch that one. I have no idea what my relative minimum right there would be. That's why this is more of a sketch. It's somewhere down there. I don't know how far down it goes. We would need some calculus or more information for that. But that is at least a sketch of what it would look like. So if you have a multiplicity that's not 1, other things happen at the axis. So again, these are both still intercepts. I'm still intersecting the axis. An intersection is not a passing through of something. Think about a street intersection. Okay, so if 2 streets intersect, they can intersect like that, right? And that right there is actually the intersection where the stoplights and stuff are, right? But you can also have an intersection that looks like this. And there's the intersection, but this street doesn't actually pass through the other one, right? It just kind of hits it. But that's still an intersection. Same thing as going like this. That's still an intersection right there. So this is still intersecting the x-axis. It's just bouncing right back off. Okay, so don't think about an intersection as a passing through, because that can throw off you understanding some other things. All right, so here's what happens here. Since it bounces off, and we use the word bounce off sometimes when we're sketching things, but how is this, if this function right here, just in this little neighborhood right here, is touching the x-axis at exactly 1 point, then how can we talk about their relationship? What kind of line touches something at exactly what, or intersects at exactly 1 point? That's 2. What's the other one? Tangent. It's tangent to it, right? Now, is this axis tangent to the whole function? No, but it's tangent to it in that little neighborhood of points. That's what I was talking about the other day. All right, so this, when you have a multiplicity that is even, the graph is tangent. It means it bounces off. Tangent to the x-axis at that 0. Okay, that's how you get the bounce. Then if the multiplicity is 1, like it was on 0, then we can't just say, oh, God, I always grab the wrong freaking thing. And the multiplicity is 1 like it was here. We can't just say it intersects because the other one intersects also. The graph passes through the x-axis at that 0. When the multiplicity is odd and greater than 1, so if the multiplicity was 3, 5, 7, whatever, then the graph has a point of inflection on the x-axis at that 0. Right now, if you are looking at a multiple choice type of situation, if when we're doing this stuff in AP Classroom or whatever, if your only options are tangent or passing through, if it has a point of inflection, like this is my axis, and it has a point of inflection at the axis, isn't it also passing through? So basically all the odd ones pass through, but if it's greater than 1 in odd, then it also has a point of inflection. So it could be answered like, it could be asked a couple of different ways is what I'm saying. Like if you don't have the option of point of inflection and your only option is passing through, then that would be the best answer for that part right there. But a point of inflection still just passes through, it doesn't bounce back off. Okay. All right, so let's look at how we're going to be asked this right now. So it says, identify the zeros, their multiplicities, and describe the effect on the graph. Well, this is nice. It's already factored for us. So since it's factored for us, we can just factor zeros. This one right here gives me 1. This one gives me 3/2. This one gives me -4. Okay. When you put them in a list, really officially in what we just did as well, but in a chart, anything else, they should always be least to greatest. So this would be -4. What would the next one be? 1, and then 3/2. All right. And then what is the multiplicity on -4? 1. What's the multiplicity on 1? 2. And on 3/2? 2. Okay. All right, so when on -4, when my multiplicity is 1, what does that mean is happening at that point on the graph? It's going through. So we say it passes through. And I know it's not big enough. Sorry, just make it work. Right, when my multiplicity is 2, what effect does that have on the graph? It's tangent, so these next two are both tangent. Okay with that? All right, good. All right, so then on number 10, go ahead and factor it. Find your zeros, fill out your chart. All right, when you're done, you check yourself with me, see if you agree. And if you had to wait for me to scribble down the factoring and the zeros, that should be a point of concern for you. All right, any questions at all? We good? We understand how all that works? Okay, beautiful. All right, so now we're going to talk about complex zeros and irrational zeros. So can anybody give me an example of an irrational number? Pi, okay. Sorry, what? Did I hear something else? Did I hear E? I thought I heard it. Okay, you're afraid to say it again. I just wasn't sure if that's what I heard. E, pi and E work. Anything else? Can you describe to me, so those are good examples. Sometimes I can get examples and not like really what it is. What's the difference between an irrational and a rational number? Can anybody tell me that? So yeah, it doesn't repeat, which means, and since it doesn't, so pi goes on forever, right? We all know that, or at least comfortable with that. 0.3 repeating goes on forever, right? But 0.3 repeating is a rational number because it repeats, and because I can write it as 1/3. Okay, if you can write a number as a ratio, it's rational. That's where the word rational comes from, ratio and rational. So if it's irrational, that means you cannot write it as a ratio of two numbers. All right, so with pi, I can put 22/7, but that's an estimation and a bad one at that. But either way, so your irrational numbers could also be like the square, they could also be square roots. So pi and E are great examples, square roots are great examples, and other, just decimals that happen, okay? So those are your irrational numbers, and then complex solutions incorporate our imaginary numbers. So we're going to do just a little bit more quick factoring, and I am going quickly through the factoring because we should be pros at factoring. This is a fourth degree polynomial, but it's set up like a quadratic, so we can treat it like a quadratic. So 0 equals, then I can, my board's being weird. I can start here because a is 1, so I know I have x squared and x squared. 12 is negative, so the signs are opposite. What would my positive number be? 2, and my negative number, 6. Okay. Can I factor this anymore? No. So since I can't factor it anymore, I'm going to go ahead and solve. And when I'm solving like this, it kind of helps to sort of organize things a little bit so it's not random stuff all over the place. So I've got x squared plus 2 equals 0. So x squared equals negative 2. So what does x equal? Plus or minus, what? Is it 2i? Square root of 2i. I'm going to write it as I times the square root of 2, and then I'll tell you why. Square root of 2i is fine. It's not wrong. But if you get sloppy and you have like square root of 2 and then you put I here and you can't tell if I is under the square root or not, that could cause you issues. So when you're writing stuff out, just like you always put the variables last, it's safest to always put the square roots last so there's no question about what's underneath it. Make sense to you? Not wrong the other way, but you better be very clear about what's under that square root and what's not. Okay? And then here, x squared minus 6 equals 0. So x squared equals 6. So x equals what? Plus or minus square root of 6. Do I need an I on that one? No. So overall then, my zeros are plus or minus I times the square root of 2 and plus or minus the square root of 6. This is a fourth degree polynomial. I have 4 roots, 4 zeros, 4 solutions. 2 of them are imaginary, 2 of them are real, all of them are irrational. Okay, we good? All right, let's look at number 2. So do I have a GCF here? No, I don't. Wish I did, but I don't. So that makes this negative 32. 2 numbers that multiply to give me negative 32 combine to give me positive 31. 32 and negative 1. So I get 4x to the 4th plus 32x squared minus x squared minus 8. Then I'm going to group. 0 equals, I'm not losing the fact that I have an equation, 4x squared then I have x squared plus 8. Here I have to factor out a negative 1, leaves me with x squared plus 8. So then this leaves me with 4x squared minus 1, and then x squared plus 8. Can I factor this anymore? Yes, both of them? No, just the first one. So 0 equals, this is a difference of squares, so I get 2x plus 1 times 2x minus 1 times x squared plus 8. So then I'm going to split this up so that my stuff doesn't get all jumbled. That can really help you, especially if you have crazy handwriting and your stuff is usually all over the place. The more you can kind of section things off for yourself, probably the better that it is. So this here, I get 2x plus 1 equals 0. So 2x equals negative 1. X equals negative 1/2. We should be comfortable enough with factoring and solving that the majority of you should be able to go from here to here accurately, and that's fine. You don't necessarily have to do these 2 steps, but some of you probably need to, and there's always some people that don't necessarily need to, but they do anyway because they're afraid not to, because they're afraid they're going to make weird mistakes. So whatever works for you is fine. So here, if I can at least skip that first step, I know that it means 2x equals 1, so x equals 1/2. Right? On things like this, you may not want to skip steps just because you can make weird sign errors, but here I get x squared plus 8 equals 0. So x squared equals negative 8. So when I take the square root, I get x equals plus or minus I times the square root of 8, but we're not done. I have to simplify that square root. What does the square root of 8 simplify down to? Good, 2 squared to 2. So I would write this as x equals plus or minus 2I times the square root of 2. Okay? We good on that? So when I list them all out, I would say x equals, now I can list these 2 separately, but I could also say plus or minus 1/2, that's fine. And then I have plus or minus 2I times the square root of 2. So 4 zeros here, 2 imaginary, 2 real. 2 of the imaginary ones are also irrational. Okay, we good? Questions? Alrighty, so then let's look at number 4. I know there's no number 3. Never question the numbering. It might be all over the place. It's irrelevant. All right, no GCF, but I do have 4 terms, so I'm going to factor by grouping, and it's already split. That's great. So I can factor out an x squared. Leaves me with x minus 5. Then what can I factor out of these 2? 16. Leaves me with x minus 5. And 0 equals, so this will give me x squared plus 16 times x minus 5. So, can I factor any more? No, I cannot. So I'm going to split this up. Let's split this up. And this gives me x squared equals negative 16. So x is equal to plus or minus what? 4i. And then I get x equals 5. So overall, x is equal to plus or minus 4i and 5. This is a cubic. 3 zeros, 2 of them are imaginary, 1 of them is real. So it could still kind of look like what we drew on the front. It could still kind of look like that, but it would mean that the axis would just be down here. It would only intersect like right there. Okay. All right. Any questions at all? All right. Good review. Let's talk about some things that kind of go along with this to solidify it a little bit. So the fundamental theorem of algebra says this. It says that a polynomial function of degree n, where n is greater than 1, has at least one zero, I think is what I want to say. Let me make sure, yeah. 0 in the complex number system. Okay? So at least 1 0 in the complex number system. So I want you to think about what that says. A polynomial function of degree n, so whatever it is, a polynomial function, okay, has at least 1 0 in the complex number system. So that means that if I have a parabola, and it looks like this, right, I have 2 real zeros. Yes? Did you agree with that? Okay. This right here says that it has to have at least 1 0 in the complex number system, which means that these are complex zeros. If your understanding of what complex numbers are is 100% tied to imaginary numbers, you need to untie it, okay? Now, and I can understand why it might be tied that way. Most likely, the first time you talk about complex numbers is when you talk about imaginary numbers. So then in your brain, complex numbers are imaginary numbers. You with me on that? Like, I get how that can kind of go together. But I want to show you this little Venn diagram here, or this big Venn diagram. So here's the complex number system. This is the big one, all right? Inside the complex number system lives the real numbers and imaginary numbers. So both are complex numbers, all right? So imaginary numbers, these are where you have the I in there, right? Complex numbers, or real numbers, it has that also, but there's a 0 there. And then that's where we have rational numbers, integers, whole numbers, natural numbers, irrational numbers. Remember, your irrational can be like the square root of 2 or pi. Rational numbers, anything you can write as a fraction. All right, so complex numbers is really just the world of all numbers you understand. Okay, so what that tells me then is this. So when we look at this, here's how I want you to make sure you understand this. A complex number can be written as like a plus or minus bi. Okay? Once you start talking about complex numbers and imaginary numbers, that is introduced to you. So if I make up some number like 2 plus 3i, okay, let's say that one. So that means that here a is 2, b is 3. We agree with that? So if I said that we're going to make a equal to, so instead of 2, I'm going to have a 0 plus 3i. That's how I get a pure imaginary number with just an I on it, okay, when a is 0. If b is equal to 0, then that would give me, and so that would mean 3 would be 0 instead of 3. So I get 2 plus 0i, which would just give me 2. So every number that is every real number is a complex number. It's just that the imaginary part is 0, okay? So complex and imaginary aren't the exact same thing. I just want to make sure that that's clear so it doesn't confuse other things. We good with that? All right, so then the last thing we have right here is the conjugate root theorem. And then it goes on to say the conjugate, so I have the conjugate root theorem, and then I say the conjugate zeros theorem. Those two words are different. Does it matter? Are those the same thing? Yes. Okay, so it depends on where you get the information from and whatever, but they could be either one. That's why I just left it as being different. The conjugate zeros theorem says, and the word conjugate shouldn't be new, states that if a complex number, specifically something like a plus bi, but then I left off something, we have to say that b cannot equal 0. That means it's not just a complex number, but it's a complex number that has an imaginary part to it, is a 0 of a polynomial with real coefficients, okay, which means it's a polynomial. Then the complex conjugate of that number. So conjugates you did when you were rationalizing things for sure and should have talked about them with these. But the conjugate to a plus bi would be a minus bi. is also a 0 of the polynomial. So here's what this is saying. If you have an imaginary 0, you have to have at least 2. They come in pairs, okay? So if we look back up here, notice that all of these, with the i's, they all had pairs, okay? Now some of the other ones did too, but here I didn't have a pair for this one, but I did for this one, okay? So if 4i is a 0, negative 4i also has to be a 0. So that kind of question, that question could be asked of you, like if I said, this is at least a sum, maybe all of the zeros of some polynomial. And I said we have 2, negative 7, and 3i. And the question is, what is the smallest degree that this polynomial could be? Could this be a third degree polynomial? Why couldn't it be? Because of the I. If 3i is a 0, what also has to be a 0? Negative 3i, right? The conjugate. So if 3i, it can't just be 3i. It's plus or minus 3i. So the smallest degree I could have would be a fourth degree. Does that make sense? It could not be a third degree. It would have to be at least a fourth degree, and maybe some others are missing and we don't know about it. Okay? So remember, they come in pairs. The imaginaries come in pairs. We good? Okay. Questions? All right. And so your assignment is where? Delta Math. And where do you go to find that? Class link. Yes, if only I had told you that before.